So the next iterative method we will talk about is called the Gauss-Seidel iterations. Okay. Gauss-Seidel iterations. And this iteration is an enhancement of the Jacobi iteration. So it's very similar to the Jacobi iteration logic, but there are slightly enhancements. Enhancement of the Jacobi iteration. The enhancement, the consequence of the Gauss-Seidel iteration as compared to the Jacobi iteration is that the Gauss-Seidel iteration will be converged faster and more stable. Converge faster and more stable. Okay, and let's check how the Gauss-Seidel iteration works as a comparison with the Jacobi iteration with the same examples we showed before. Okay, so before we have our system be doing the Jacobi looping, which is xk plus 1 equals to yk divided by 4 minus zk divided by 4 plus 7 over 4 yk plus 1 equals 2 minus half of xk minus 1 over 8 zk plus, minus 21 divided by 8. Zk plus 1 equals 2, 1 over 5 xk minus 1 over 5 yk plus 3. So this is 2 over 5. Okay. So this is our previous Jacobi iteration. This is the Jacobi. And then let's see how the Gauss-Seidel works. So the Gauss-Seidel is basically use the previous existed updated value into the next looping so that it can converge faster and more stable. So the Gauss-Seidel, let's just represent by the GS, is use the solution from earlier rows for later rows. Then it will reach convergence faster and more stable. So use the solution from the previous row, for example, xk plus 1, and it will represent xk plus 1 here. So use the solution from previous rows for the later rows. Then how we write the Gauss-Seidel iteration. So for the Gauss-Seidel iteration, the xk plus 1 is unchanged. Okay, it's unchanged. Will be 1 over 4 by k minus 1 over 4 zk plus 7 over 4 because there is no previous row solved. Then the next one will be yk plus 1 and will be equals to negative half. Instead of xk, we have xk plus 1 because xk plus 1 already solved from the previous rows. Then we minus 1 over 8 zk minus 21 divided by 8. Why the zk is not updated? Because there is no previous row solved for the zk. Okay. Then let's go to the zk plus 1. That will be equals to 2 over 5 xk plus 1, which is solved by the first row, minus 1 over 5 yk plus 1, which is solved by the second row, plus 3. So you can see that all the previous row solved values will be applied to the later row. That is the difference between the Gauss-Seidel iteration as well as compared to the Jacobi iteration. And to solve, let's use a state space representation to represent the Gauss-Seidel iteration. So to solve the AX equals to B, we will still use 3 parts to represent my A. So A is equals to L plus U plus D. So the L and the U, which is represent. So this is your A system. Here is your diagonal element. Here is your lower triangular element. And here is the upper triangular element. So the A matrices can be a sum of all these three parts. Okay. Then what is our Gauss-Seidel? What is our Jacobi iteration before? So the Jacobi iteration, which is xk plus 1, will be equals to B inverse B, sorry, B vector minus L xk minus U xk. Okay, so this is our Jacobi iterations. We just simply separate the variables and do the looping. But for the Gauss-Seidel, we want to use, for example, the previous solutions already solved by the previous rows. So basically, for the lower triangular, if you can see that the lower triangular value, you will always have the updated value here. So updated value here, updated value here. Then for the Gauss-Seidel iteration, for the lower triangular operates on the solution, it should be the updated solution. So it should be xk plus 1 here, xk plus 1. Then what you have the d xk plus 1 equals to b minus l xk plus 1 minus u xk. This k is unchanged because in the upper triangular part, the value is not updated yet from the previous row. So you can shift this part to the left. Then what you have d plus l x k plus 1 equals to b minus u x k. Okay, so you put all the components with the x k plus 1 into the left, then the right part will be b minus u x k. Then what you have for the xk plus 1, which is the current looping value, will be equals to b plus l inverse b minus d plus l inverse u x k. Okay. So this is the looping for the Gauss-Seidel. This is the Gauss-Seidel looping, which is xk plus 1 equals to d plus l inverse b minus d plus l inverse u xk. We can also write about the arrows for each looping. So the arrow of the current iteration step will be equal to minus d plus l inverse u arrow at the previous step. So this is the arrow analysis for the Gauss-Seidel. This is the arrow compared to the true value. This is for the next step.